Okay, fellow engineers, you are welcome to part 2 of the water tank design. As you remember, the last time we applied our loads. After modeling, we applied our loads. We did the load combinations, and we also looked at our settings. Like you come under analysis, these are settings for concrete. So today we are going to move directly to running the analysis and looking at the results. Okay, so we will go directly to this properties browser. As you can see here, we have the model. Next is analysis. So we are going to click on analysis like this. Under analysis, we have verify, mesh, evaluate, finite element calculation, push over calculation. Anyway, this stuff that has to do with some earthquakes and all of this stuff. We are not performing that. We did not specify that for our model. So let's see how it goes. So normally what we want to do is to mesh the building first. We want to carry out the finite element meshing to be able to know if there are elements that are not well connected within themselves. So that's why we are just going to select right up to maybe, let's say, mesh, and then we are going to say okay. So you see the element has been meshed and there are no errors. You can turn it around to see the meshing. This is rectangular meshing. Remember, when we came here to mesh options, we put our mesh to be 0.3. So this is 0.3, 0.3. It's a rectangular meshing. That's why you can see here, this is a pillar, a column, 3 meters. 3 divided by 0.3 gives us 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's how it works. Okay, you can right click and turn off display mesh if you don't want the mesh. Okay, you can right click and click display mesh. Your mesh will come on. You can click display knots, the knots of the mesh, so you can play around with it. Now, given that there is no problem with our mesh, we are going to come back to our model and then click on analysis again, and we are going to create a new analysis model. This time around we are going to launch the calculation right up to the RC calculation, reinforced concrete calculation, and we are going to click on OK. The analysis is running. Okay, the analysis is finished, and here on the command line on the information center we have a couple of stuff there. Okay, as you can see, these are warnings, not errors. So we don't have any problem with that. And the warnings are about cracks. Remember that I used 3 load combinations. There was the serviceable, the ultimate, and the quasi-permanent. That's why you are seeing case 106. Case 106 is a quasi-permanent combination which I'm using to do what? Verification of cracks. So like here the crack limit is 0.4, but they are telling me that the element has up to 0.7. So like I said earlier, these are warnings, these are not errors, so somehow they can be ignored for a while. But when we are going to be doing detailed stuff, we will see somehow how we can play around. So back to our model. This is my model that has been calculated. I'm going to right click and I'm gonna turn off this mesh to have something like this. Okay, now we are going to view the results. For example, as soon as my model is calculated, this results tab becomes active, and under results tab I have first save values, save views, meaning that these are like here. These saved views that I have here, remember when I took photos, these are the views that were saved before analysis. Now any view that I save now will be referred to as a view after analysis or post processing view. That's what, so you appear somewhere here under post processing. Okay, you can see here your load cases, and you can see here your load combinations. So now let's look at what is going on in this tab here. When you come to finite element results, you can see that you have footings, linear elements, and planar elements. So here is joints. Okay, on supports you have your fellows down here. Then under loads, under forces, you have displacements, forces, stresses, and resultant forces. This is the load. So like for example, if I select displacement under forces and I select 1L, 1L means what I'm basically doing is I want the displacements produced by the live load. That's what I mean, because L is a live load. So I want the displacements produced by the live load. Now I'm going to tell the computer on which element. So like if I come here to support elements, you see it is put to none. So if I go to the linear elements, you can see it is put to G. So if I go to the planar elements, it is also put to G. So what I've basically told the software is, give me the displacement produced by the live load on the linear elements and on the planar elements. Ignore the supports. Again, you can see I have asked the software to give me in vector form. As well, I could ask the software to give in value form. You see, remember this is for the supports. That's why when I change it to values, you do not see any change here. Let's go to the linear element. Let's transform it to values. You see, these are the values. It is changed to values. So when you look here, they are telling you that the largest displacement is 0.034 centimeters. That's what they are telling you. So if you have a model that you have let's say G plus 10, you want to limit the displacements to a particular value, this table is gonna help you very much. Okay, So if I go to the planar elements and I say give me the values that's on the floors, so I can turn off the values for the, let me say, diagrams, say colors, deformed. Let me turn off the values for this fellow. So these are the values of the displacements for the floor. The thing is really bogus. So when you look here on your right, on your left, you have the possibility of increasing, look, increasing the size of the values. You can reduce. See, you can increase the size of the text as well as you can reduce. We are going to come to this. So let me say I want the displacement due to the combination at the ultimate limit state. You see, the ultimate limit state is combination 102. That's where you have 1.35 D is the dead load plus 1.5 L, which is the live load. So I'm gonna click here, and you are gonna see that the largest displacement due to the ultimate limit state, which is producing the highest load, is 0.288 centimeters, not up to 1 centimeter. So that's very beautiful. Now I can look at diagrams. You see, these are the diagrams. I can also go to floors and say give me the diagrams, where X diagrams, you see, give me the Y diagrams of the displacements. Let me say give me, where's none? I'm looking for none. Oh, what's happening? Just give me values, or I can basically just turn this off. So these are the displacements on the linear elements in the X direction at the ultimate limit state combination. So there's something that's very important here that you must always check on, which is the axial loads or the loads on the support. Is something very important because it is on those loads that you design your foundation. Okay, so I'm going to turn this to none. Okay, I already have my ultimate limit state selected. I'm going to leave from displacement to forces. So I want the forces produced by the ultimate limit, by the ultimate limit combination, and I want those forces on the supports, and I want the forces on the supports in the Z direction, vertically. Wow. So when you do that, you will see that on each support there are pointers, and these pointers have different colors. And if you come here to this table, you are going to see that your axial loads are ranging from 151.1 kilonewton to 291.2 kilonewton. So the smallest guy here is 291.2, and the largest guy is 151.1 kilonewton. You can see negative has been added to this value because they are telling you that they are going down. Okay, now the sizes, so the sizes of these guys, let me increase them like this. You see, that's the reason for this second guy. The sizes are showing you the columns that are most loaded, and you can see that these two columns are most loaded. Now, how do we know the value here? Yeah, we know that you've seen that they are most loaded, but How about their values? What's the value of the forces? So we are going to go over here to result settings and click on it, and we are going to select under forces, because forces is what is active. We are going to select our point support. Inside of point support, we are going to select FZ. As we select FZ, we are going to come over here under display mode, and we tell our software we need values. We don't need vectors, but we need values, and then we are gonna click OK. Wow. And as you can see, the pointers have been changed to values. The pointers have been changed to values. And as you can see, like I was telling you, our loads are ranging from 151 to 291. Like I told you, these two pillars are most loaded. Let me increase the size of the text like this. You can see better. Like this. So if I go over here to Home tab and I place myself in a plan view, look at it. So you can see each footing and the value. So these two footings have the same value of 291.2 kilonewton, negative 291.2. Why? Because the force is acting in a different sense to our positive z-axis. Okay. Wow. You can see the law of symmetry, because the loads were symmetrical. That's why these two pillars have the same load, these two have the same load, and these two have the same load. I'll go back to 3D like this. Wow. Okay. That was some form of visualization, analysis and visualization. So now, how do we go about designing elements? I'm gonna come over back to my Home tab. I will change from render, from axis to profiles, and then I will change from linear contour to what? Let me say shaded faces. So I want to see my model like this. Remember, we are still inside visualization of results. So the model is still calculated. It's not as if I've turned off I've cancelled the calculations. So this is it. Okay. Personally, I always start by calculating columns. How do we do it? Like I told you, when you install GRAITEC, there are 3 files that appear on your screen. You have GRAITEC Advanced Design. This is 2025. GRAITEC Advanced Design America AGA 2025. Then you have GRAITEC Models 2025. Okay, what does it mean by GRAITEC models? Modules. This I'm calling it wrongly. Forgive my expression. It is module, not model. Module. Okay, so these modules are like independent subprograms under the main GRAITEC, which is what we are open. This is what I'm referring to as the main GRAITEC. These modules are acting as they are independent from the main GRAITEC model. Okay, suppose that I have a model in a tabs that I've analyzed, and I have the reactions at the base of a column, and I want to design that column using GRAITEC. I don't need to come and remodel the model in GRAITEC in order to have the reactions at the base of that column. What I need to do is simply to open a GRAITEC column module, like this is RC column. I can launch this RC column. So I launch the RC column module of GRAITEC. When the RC column module of GRAITEC has been launched, I am going to select a type of column that I want. Maybe is not template. Yes, okay, no problem. Let me select an unorthodox, column like this. This is a column. This is a triangular column. So now I'm now presuming that my model in ETABS had triangular columns. So I will come over here to load cases. I will have to enter the load cases because my model is coming from a tab. I'll come over to combination. I will enter my combinations. I'll come over to my loads and I will go to a tabs and look at my different loads and I will enter them here manually. That means the normal loads, the moments, these are my normal loads, the moments in the different directions, the shear forces in the different directions before even the position of my force. Is it directly at the center or there is an eccentricity? So these are the top forces and the bottom forces. If my model was coming from GRAITEC, this is what I will do before moving on to set up the reinforcement and calculate. But now I have a model here that is designed in advanced design. So what I'm going to do is simply to call up the model, the module, the column module, to calculate the column that I'm going to select now. So if I want to calculate this column, given that it is the most loaded, I'm gonna select the column. I will right click, then I will call up the advanced design module. So exporting to advanced design module, look at what will happen. It will automatically activate or call up the GRAITEC module. You see, when it calls up the GRAITEC module, my column will appear here having the characteristics. So what the GRAITEC module has done is that it has detected my column. Not only has it detected my column, but it has also detected the different loads on the column. Like if you look here, you will see 184, all of this and all of this. Remember, this is at the serviceable limit. That's why you have the loads like this. Because we know that at the ultimate limit it is 291. So this is 180 something. When you combine and combine, you reach up to 291. So now my column has been called up with all its characteristics. As you can see, the column, this is the column and these are the ground beams linked to that column. So what I need to do now is simply to set up not more the load cases, because the load cases have already come in. 1.5, 1.35, as you can see. Not more the combinations, because the combinations have already automatically been detected. Not more the loads, because as you can see, the loads have automatically been detected. These are the loads here. And if you look at the bottom loads, you will see them here. Okay. All right. You can see this is top load 184.8. Remember, this is at SLS. That's why you have 1L and D. Remember. Okay. When you go to bottom, this is 184. When you go to bottom, you have 187. What's the matter? The weight of the column has been added. That's the matter. Okay. You even have a possibility of exporting your loads to Excel. All right. I'll say okay. So all of this has been automatically detected from GRAITEC. Now we need to set up this. We start by our design, because even the geometry of the pillar of the column has been detected from GRAITEC. The buckling properties have been detected from GRAITEC. You don't need to set that up. So what we need to do is to set up this section, then set up this section. Let's see how it's going. Let's start with design assumptions. So these are some stuff that you have to set here. Relative humidity, I will leave it at 50. It's a normal column, relatively exposed, so it's more like, think of a column inside of a building. Let's see that way. It's not exposed to humidity and all of stuff. Concrete loading age 28 days. Okay. Concrete shrinkage, let's say shrinkage starts at 2 days. Cement class normal. We have different cement classes here. So let's go to column design. All of this you are going to take time to look at them yourselves, but I want to show you what I usually do. This is seismic. I always turn this off because I'm in Cameroon and we don't have earthquakes in Cameroon. This is fire resistance. Remember that this concrete is column is a ground column, so I have no need to be looking at the fire resistance of the column. Reinforcement, reinforced concrete, C2530, yes. Aggregate size, I will take 25. So here I'm considering that I'm using gravel of 1525. All of this other stuff I will just leave it. I'm not using a high strength concrete, neither am I using a silica or confined concrete. I'll take this. Exposure class. So now this concrete is in the ground. The exposure cannot be X0. The exposure will be something like X2, XC2. So this is normally the exposure class for elements which are in contact with the ground. While X0 is the exposure class for elements which are not in contact with the ground. This is just like a starting point, the basic. But you have to do a structural class for each element depending on the level of exposure of that element. Yes. So that element is exposed to that environment for a long term. Yes. Concrete covers. So this is where you set your concrete covers. And there's something here that's important. Structural class. So what does it mean by structural class? In Eurocodes we have up to S6. Structural class is depending on the type of structure. Okay, this structure that we have right now is just a common structure. Our cement is a common cement. But suppose that we're building something like a bridge. Okay, we have piers that are going to be inside the river. Those piers may be at the concrete may be attacked by violent chemical elements. So we cannot use a common cement. That's the first thing. And the type of cement influences the structural class. Secondly, something like a building has a 50-year lifespan design. Now, how about a bridge? You can't design a bridge with a lifespan of 50 years. No. So, the type of element, its lifespan, influences what? The structural class. But as, let me say, a baseline for common structures, S4 is the structural class. So you have a building, normal structures, your structural class is going to normally be S4. So that's why we are going to leave S4 and we are going to say apply. Okay, we are going now to look at our reinforcement diameters. Remember when I was designing my structures, I asked the structures, the software, to use diameter 10 and diameter 12. So for my longitudinal rods, I'm just going to leave diameter 10 and 12, and then I will leave diameter 6 for my transversal reinforcement, for my stirrup. These are my nominal diameters and these are my real diameters. So what I'm gonna do is, sometimes I like changing this to the same size as the nominal diameters, like 8 and then 10, 12. So I can allow it here because these other guys I'm not going to use them. But if you look at the section area, you see that the section area is following what? A nominal diameter. So okay, I allow it that way. Let's go now to reinforcement assumptions. The first thing you want to do is you want to look at longitudinal reinforcement. And under longitudinal reinforcement, you can see the software has selected diameter 10. Hooks. Provide hooks for diameters less than 10. No problem. Let's start from up this way. The first thing is that the software has chosen to reinforce the column with minimum number of bars. If you click down here, you can see there's also the solution with minimum available bars diameter. There's also a solution with user defined. Okay, we are going to come to that. Spacing, minimum spacing 50. Bars cut off at bottom. So your bars are normally just going to be straight down to the bottom. If you look down here, you can see bars cut off at top, which means the bars will not extend up. That's what I mean. Anchorage length. So let me just rush over this. As you, as an engineer, you are going over this, you will take your time and look over each table and watch and play with it and see what is coming up. So if I want a maximum spacing, I can select here and then give the maximum spacing. For now, I'm just going to leave the software to do the choosing. Transversal reinforcements. Okay, what did I say? So what is basically happening here is that the software has chosen to use diameter 10. Remember, I selected diameter 10 and diameter 12 for the longitudinal bars, but the software has chosen diameter 10 first, and it is going to provide hooks. These hooks are going to be diameter 6 because we choose diameter 6 for the hooks, and are going to be bent at 135. So you can choose 90, negative, 180, as it depends on you. So you can impose hooks on the top, like somewhere around here you can impose. I have 5. I impose the diameter, provide safety links. Okay, transversal rods, you can see transversal bars is diameter 6, 135. You can take 90, depends on you. Minimum theoretical area steel binders, we don't have this, we don't allow that. Maximum spacing 400, that's 40 centimeters. I just want to put my maximum spacing maybe to something like 250. Yeah, you can go with the option of uniform spacing, and then give, depends on you, but can even go with spacing as multiple of imposed value. I don't. So I want to rush over this. I put my maximum at 250, bottom link offset 50, top link offset 50. Starter bars, you have something like this, diameter 10. Consider the starter bars in the rebar list. So when the software wants to produce your schedule, your bar schedule, it is going to consider this, meaning the stirrup here and the bars length is going to be added to your total number of bars. Seismic effective length, all of this bar length can come here. Leave it at anchorage length. Longitudinal bars, transversal bars, provide transversal bars, bottom spacing. So this we are not going to look at this. Like, you know, if you press top, you see what is happening. You press bottom, you see what it's doing. You press top and bottom. So what I'm going to do, I don't want them, allow it like that. Oh, was that what was there? I thought it was bottom, then I yeah, bottom bars, bottom starter bars. Basically we don't need this, so that's why we have set no starter bars. If you want, you can put. So we do not need this. We are going to say apply. OK, let's see what's happening here. This guy, we are just going to allow him. This guy verify is going to be very useful if you are working with a column from a different software. So here we don't need to touch this. We are going to move directly to our calculations. So we are going to click. So we are going to click on calculate, and you can see that our column has been calculated, and you can see under here, when you look at errors, you see there are no calculation errors. There are no calculation errors. When you look at calculation results, you are going to see a calculation result. So you must be sure that there are no errors. So the column has been calculated. Unfortunately, there are some guys outside that are making noise. Probably they want to fight, and this is 2 a.m. and they want to fight at 2 a.m. Ah, God have mercy. Okay, I pray no one gets hurt. I pray people learn to read their Bibles, to know that he who is soon angry is not wise. People have to read their Bibles to know that he who is soon angry is not wise. Okay, engineers, let's continue. So this is my column that have been calculated with 4 bars. Sometimes this 4 bars is not very nice to me. Suppose I wanted 6 bars. I will go to reinforcement assumption. I will go to my longitudinal rods, reinforcement, and inside of reinforcement solution, I'm going to choose user defined number of bars, and then here, whoa, what was that? Okay, then number of bars in the x direction, I can put 3, and then I will say okay, and then I will recalculate, and then you can see I have 3 reinforcement. You can see it's 3 beds. So what I'll do is I'll just go with what the software produced, which is 2, and I'll calculate, and this is it. So now I'll go to my results. Inside of my results, you can see your interactive curves. These are your interactive curves. So you can see all your efforts, your forces are inside the cone of forces here. Okay, you can see your moment diagrams. You can see you are drawing. When you click on drawing, then the software is going to generate the drawing on a paper. So this is your footing that has been generated, your pillar that has been generated on a paper with sections and the concrete. You see the project water tank design, drawing name P, position column 1, level 1. All right, so I did not set the number of the project, I did not set the phase, I did not set the date. You see, okay, it's a linear element. So when you come here to your bar schedule, you can look at your bar schedule. So down here you can have your section elevation, and section B. So what do you do? This is a paper. How do you have it like ready for printing? You come over here. There's something you have to set down here under printer settings. You see my printer has been set to Xerox VersaLink. I don't want this. I want to print it as a PDF. So I will set it to my Nitro PDF Creator Nitro Pro 11. Secondly, I will click on this to set up the paper size. So I'll come to pages. First, I want it to be portrait, so vertical. Then I'll go under my page size. You can see here is letter. I want to go to open and choose A4 like this and say okay. Then the next thing I want to do is to ask the software to fit the drawing on the paper like this. After fitting, then the next thing I will do is simply to right click on this and then print. So let me save it on my desktop. I will call it I'll call it PP, and I will save. So engineers as okay, So this is my column that has been printed to Nitro. This is a PDF which I can send to be printed and taken to the site for execution. So that's the first thing. The second thing is the report of this column. I think reporting I should do it in another video. So let me show you a quick move on how to calculate the footing. So this is the footing. I'll click on the footing. As I click on the footing, I export. As it is exporting to my footing model, I'll be patient for it to export to load the module. So this is the footing that has been loaded. As the footing has been loaded, I will set it up. Footing type, I can check the footing type from here. I will just leave it at a rectangular footing. The geometry, so this is where I normally set the dimensions of the footing. So I will leave it at 1 meter by 30 centimeters. So if I want a footing that has this glasses or bevel cuts, what I will do is I will click on bevel cuts and then I will set them up. We are going to come back to this. So let's say my footing is like in our project, our footing was 1 meter in the ground. Was it 1 meter? Yes, I think it was 1 meter in the ground when we were setting up our levels. Yes, so I'll put here, given that my footing is 1 meter in the ground, I will put now negative, remember it is in millimeters, negative 700. So this negative 700 is this level. So when you take this level, which is negative 700 plus 300, which is the thickness of the footing, it will give you negative 1000 here, which is the level at Z2. So this is Z1. Z1 is the top of the footing and Z2 is the bottom of the footing. If you look here very well, you will see that by default the top of the footing is at the same level with the top of the ground. That is why the bottom of the footing is here at 300. So, but as soon as I set the top of the footing at negative 700, the bottom will also change. You see, as I press enter, the bottom has changed to negative 1000. These guys here, I won't touch them. Supported element. This is the element that is sitting on the footing. So our software has already detected that that element is 250 by 250 and it has given it an imaginative height of 400. This is just for representative purposes, because actually the loads that are coming down due to these elements and the other elements has already been taken into account. As you can see here, these are loads. All right, as you can see, these are the loads. Okay, and when you look very well, it's the same load that we had at the bottom of the column, 187. So that's the load that's falling on the footing. So let's go to supported element projection. So this is how this element is sitting on the footing. Right now The element is sitting in the middle of the footing at the center. So by manipulating these values, you can shift the element to sit at the edge. So if I put M to be 0, let me say I put M to be 0, let's see what goes on. It means I'm telling my software that this element, this is at 0, means that this element is sitting here. That is why L has gone up to 750. So if this is 1 meter long and you remove 1 meter is 1000, so when you remove 250 millimeters, which is the thickness of this column, you will be left with 750, meaning that effectively this column is sitting at the end here. That's what it means. So by modifying these values, I can end up with a column that is sitting at this end. Okay, let me bring it back to 375, meaning that I want the column to be centralized. All right. I will come back, like I told you. I'm going to do another detailed video where we are going to touch many of these parameters. So for now, I'll just go down to bedding. So do I need lean concrete at the bottom of the footing? I always like to. Let me say yes, and I'll put a lean concrete of 50 millimeters. Here I'll just say apply. Okay. Then my soil database. This is just the different types of soil that have been loaded into the software. But now you have your soil profile. Okay. What is here? They have indicated that from 0, that is from the ground level, to a depth of 300 millimeters, that's 30 centimeters, the soil that we have there is peat. It's basically just this vegetable soil, and the density is 18 kilonewton per cubic meter. That's fine. Now they are telling you that from 300 millimeters down to the end, the soil that we have is clay, mud. So that basically means from here, look at it this way, from 0 to 300 to negative 300 we have peat, from negative 300 to infinity we have mud. So what I want to do is to show you how you can change this, but you are normally going to change this based on the soil report. So if I have something like, let me just say want to take medium gravel. Let me just say medium sand, like this. Yeah, you can see the density has changed. So I will do another video. We'll see how we can take into consideration this water level and all of that. Okay, we are going to move over to design assumptions. I want to use the horizontal top branch. You know, for steel in Eurocode we have two types of strain curves. There's the horizontal and there's the incline. So the inclined top and the horizontal top, let me just remove the top, and these are the safety values. You know, at the ultimate limit we have 1.5, 1.15. This is concrete and this is steel. At the accidental 1.2, 1.2, at the seismic 1.2, 1.2. Okay, footings, footing design. So there's something important here. I want to use the strut and tie method. Another person can decide to use the bi-cantilever, but I always like to use the strut and tie method. You can, you know, play around with it and see. So there's something important here. I want the software to take into account loads and overloads. What does that mean? My footing is inside the ground. There is soil on top of that footing. So I want the software to take into account the weight of soil that is on this footing. Yeah, that's very important. Don't forget. Then, for this, I don't want this for now. So, we are just going to go to the bearing verifications. Okay. There's something that's very important which I would also like to show you. Let's see. Under bearing verifications, alright, I want to show you something that's very important. So just be patient with me. Okay. This is a report for a project I did recently. So this is LaTeX. I've typed it in LaTeX. I will come to this when we go to project reporting. So I have told, I'm telling the person reading the report that from the soil test report, the geotechnicians advised me to use a value of 2 bars for the soil strength at a depth of 2.5 meters. So here I am calculating a footing, and I have to give the value of the bearing capacity, and they are telling me by default it is calculated, but I don't want it calculated. I want to give a value that I have read from my soil test report. So I'm going to change it from the bearing resistance. I'll give it an imposed value of a bearing pressure. That's why you can see 0.5 megapascal. If I was here, you will see we are talking about kilonewton. But when I come to bearing resistance, because normally this is dependent on the type of soil, but here in Cameroon we deal mostly with the bearing strength that is calculated. So from the penetration test, they give us a value that we use at a particular depth. So I will go to imposed, meaning that I have a value that I want to enter, and then of a bearing pressure. I have the value of a bearing pressure of the soil that I want to enter. So here you can see that they are talking of curenet.dr. It is neither QULS, like the stress at the ultimate limit, or QSLS, the stress at the serviceable limit, but they are giving you a funny name here, curenet.gr. So what you need to know is there is a particular way to calculate this curenet. This curenet is derived from your serviceable stress or from your ultimate stress. Let's see how to calculate it according to Eurocode. So if that stress from your geotechnical report is 2 bars, let's say our stress is 2 bars. 2 bars is the same as 0.2 megapascal. Okay, how do we do to have curenet? Remember, these 2 bars, they have told us that it is at the serviceable limit state. So the first thing we need to do is to take this from the serviceable limit state to the ultimate limit state, and we are going to multiply by a coefficient of 1.4. Follow up. So when I take 0.2 times 1.4, I have 0.28. Okay, after having 0.28, we need to proceed to another value called the sigma RGV, and we are going to multiply the ultimate stress by 1.2. Okay, to have cure net, we are going to multiply sigma RGV by 1.4 again. So you can visit table B33 of Eurocode. Now, sigma GV, which is 0.33, when we multiply by 1.4, it gives us 0.47. So these are the steps you have to follow to be able to arrive at a value of cure net, depending on the value of your serviceable stress. So when you have your serviceable stress, you need to look for your ultimate stress by multiplying by 1.4. From your ultimate stress, you need to move to your sigma RGV by multiplying by 1.2. From your sigma RGV, you need to move to your cure net by multiplying by 1.4. So if the geotechnicians give you your ultimate stress, you just need to move directly to sigma RGV, then to cure net. If they give you the serviceable, then you move to ultimate first, then to RGV, then to cure net. So that is how we get this value of cure net. So I have here 0.47. I approximate it to 0.5. So that is the value we are going to enter into our software. So I come to my footing and I say 0.5 megapascal, 0.5. Then I go to other geotechnical verifications. I want my footing to be verified. You are going to you can do this considering earth pressure for sliding if you want. For now, we are going to look at that. So passive earth pressure mobilization, I don't want this because I'm not seeing my building likely to slide my footing. Okay, so I want overturning verification, I want eccentricity verification, I want my settlement verification. This is very important, and the settlement value, the limit, is also going to be given to you in the geotechnical report. Like here for this particular project, the limit of my settlement was given as 2.5 centimeters. So what does it mean? 2.5 centimeters is 25 millimeters. So I will simply come here and set my limit of settlement to 25 millimeters. There are a couple of methods used for calculating settlements. I always like to put the pressure meter. So multi-layer verification, all of these guys seismic. The next guy you're going to set up is the reinforcement. Reinforced concrete. So my aggregate size, I want to put it at 25. My concrete size remains C 2530. My reinforcement is S500, so that's why I'm putting here S500. Cracking, yes, allow it. Remember, your exposure class is XC2. This is the common class for elements in contact with the earth. Concrete covers, I always like to my top cover at 40, my bottom cover I always like to put it at 50, and then structural class S4. Perfect. Reinforcement, let me come to reinforcement diameter first, 10 and 12. Okay, this I will just say okay. Reinforcement assumptions, for now we're just going to go with a single mat. If I want something like this, I'm going to do this or close it up. for now. Let's just leave it the way it is. The next thing I want to do is to run the calculation like this. By running the calculation, and you can see that my footing has been calculated. There are no calculation errors, and you can see various bearing resistance verifications. You can see they have been passed. Okay, there's something very important that I want to look at. I want us to look at here. There is you can see sliding pass. All of this has passed. All of this has passed. Let me take you to the pillar. This is the column. Let's go back to model. Okay, let's look at our column for a while. There's something here that I want us to look at. Oh, actually it is not here for now. Slenderness. Okay, I will come back to it. I'll come back to it. And when we are going to come back to that detailed video, we are going to do some settings before running the analysis. What I wanted to look over here was the capacity design, because we have a column of 25 by 25. Sometimes you have a column and your column is only working at 50%. What does that mean? It's wastage of concrete. So we are going to see how to look at the working capacity of the concrete of the column, and then see if we can reduce the size or increase the size. For now, let's finish up with our column. So I can go to results, I can see analysis, I can see stability, I can see, just go directly to drawings. And this is my footing that has been generated on my paper. The settings here are the same as I did for the column, and you can see so the software choose diameter 10. Diameter 10 is fine, as you can see. So here we have 5 spacing of 17 centimeters, and here 5 spacing of 17 centimeters. So normally we have 6 bars here, as you will see. 6 bars. 5 spacing means 6 bars. Okay, you can then do all your settings here, and then right click and print to take to the site. Okay, ladies and gentlemen, I will end this part 2 here. I will come back to it. I will come back to it, because there is some detailed stuff that I want to you know, to look at it closely. I want us to look at it closely. And then there's also beams. The calculation of beams and floors, it follows the same procedure. So you can select your beam and send to your design module. And for your floors, since there is no floor module, when you select your floor, what you are going to do is open with design modules. So it is going to activate this tab here. So while waiting for the design modules to open, you can see this is the design module tab that has been opened. And you can see our foundation level, you can see floor. This is a floor. You can have another. This is the particular floor that I call up. So here, this is a model, like the formal plan. This is the reinforcement diagram, reinforcement cage, reinforcement interactive drawing. So I'm just rushing over it. So this is, remember, this is interactive drawing sheet 2. So let's go to sheet 1 and see what's going on. So this is sheet 1, reinforcement plan, bottom plan. So when you look over here, that's not yet been calculated, so that's why you see it this way. Anyway, like I told you, this is just, I'm rushing over. I'm trying to just put your mind, I'm putting your mind in you know, work mode. So normally when all this has opened, I need to set up the reinforcement diameters. I need to, you know, set up stuff here, then calculate. That's what it means. When you calculate, you will see the diameters here. This is it. This is the bottom mat. In this direction you have 18 times 20. So this is diameter 10, 5 diameter 10, space at 20 centimeters. From here to here, 5 diameter 10, space at 20. What is this? Diameter 8. So 6 diameter 8, space at 20, bottom, like this, in the X direction. What do we have here? 5 diameter 10, space at 20. So it will really take time. You have to take time and really look at this and study it and understand the writings, understand what is going on. So now if I go back to my reinforcement plan, you can see it. If I go to my what do I want, let's see, reinforcement case, look at it. Let me turn it this way like this. See what's going on. Look at what's happening. These are the bottom bars. Bottom bars. So as you can see, this is the way the element is going to be reinforced. So like I'm saying, this is a rush over. This is a very much rush over. Let me see sheet 2. Okay, this is sheet 2. Alright. So you have some bars here at the corner. They are going like this, I think. So these are diameter 8 bars, space at 150. Diameter 8 bars, space at 150 is the same. So this U bars at the extreme here. These are other U bars at the extreme here, space at 20. Alright. So ladies and gentlemen, let me leave you here for now. I will leave you here for now. Please do not be offended. Do not be offended that I am rushing over things. I will come back to this by the grace of the Lord Jesus Christ. I will come back to this, and I'm going to be more detailed in part 3. So do not be offended. Try to be someone who is always joyful. Like the Bible says, anybody who is, he that is soon angry is not wise. I am married, I have a family, have a wife, I have children. So don't be somebody that causes harm to others. If somebody works for you, pay the person. If you can't pay, go to the person and plead with the person to give you, time for you to meet up with your obligations towards him. Don't be somebody who is soon angry. If you are somebody who is quickly upset, then you are not wise. Learn to take care of yourself. One of the best ways to take care of yourself is always to be happy. Learn to respect your body. Learn to respect your body. Learn to respect others. Okay, I'm almost preaching. I'm also a pastor. I'm a prophet. So I love what is right. So do not be offended if I have done some things in a way that you did not expect. I want you to look at my motive. My motive is that I'm trying to transmit something. I may have shortcomings in transmitting the thing, but look at my general motive. My motive is to transmit that thing. So ladies and gentlemen, God bless you and keep you. See you another time.